received any yet. So, you know, some just mixed up.
What?
So that's coming in. I think we have to post some other chemistry math, so we'll have to see this stuff if you need more information on this.
That's funny.
Okay, if you are pre-med and a junior or senior, and I figured there was probably a pretty good bet there were some of those in this class. There's a required pre-med meeting coming up if you're planning to apply to medical school this spring, either as a junior or as a graduating senior, either one. And that is Monday, March 17th at 4:30 p.m. in Robinson 210. And that's being called by Dr. Stevens and Dr. Surgeon. And then also, I know that AOT is not required really to apply to medical school, but a lot of people like to take it anyway. And this is the first time ever they're going to offer it this summer, and they're going to offer the whole year sequence this summer. Yes.
Teaching it.
I don't know, but it says that you need to contact Justin Albright if you are interested. My assumption is that it's going to be offered like any summer class, and that you can just register when you register for your fall classes. But if you want more information, email him. Okay. We are in chapter 17. Which is the citric acid cycle.
No, not ready.
Not ready. Sorry. This is 8 more reactions
Wait.
that are going to oxidize acetyl coenzyme A to 2 carbon dioxides. And this is going to produce reducing equivalents. NADH and FADH2, which will be important later when we talk about how to synthesize ATP using the electron transport chain and oxidative phosphorylation. It also produces an ATP equivalent in the form of GTP. It's also known as the Krebs cycle, or the tricarboxylic acid cycle. I don't know which of those biology department's using.
Krebs cycle.
Krebs cycle.
That's what we learned in 140.
Okay. So we do have one little problem in that we haven't made acetyl coenzyme A yet. We're going to have to do that first. But here we are. This is what we have in. We've taken glycogen, we've broken it down to glucose. We've taken glucose, we've broken it down to pyruvate. Okay, and then there are these off-pathway things that if I want to, I can use fermentation to do something with the pyruvate. Or if I want to make lots of ATP, then I need to go through the citric acid cycle and make reducing equivalents for the electron transport chain later. So pyruvate has to be converted to acetyl coenzyme A first, and then that is what enters the citric acid cycle. And then once we've done the whole citric acid cycle, we will, and oxidative phosphorylation, we will go back and we'll talk about, well, okay, how do fatty acids feed into this, and how do amino acids feed into this. Okay, so that's what we're going for. occurs, and it's not the cytosol, but in the mitochondrial matrix. So, pyruvate formed in the cytosol, because that is where gluconeogenesis and glycogen breakdown is going to happen. It's transported into mitochondria. And we already mentioned that that was an anti-porter that brought pyruvate in. And our net reaction is going to be 3 NAD one FAD, one GDP, one inorganic phosphate. And I should clarify that this is once pyruvate is converted. To acetyl coenzyme A. So, one inorganic phosphate, one acetyl coenzyme A. And that's going to give me 3 NADH plus an FADH plus a GTP plus the coenzyme A plus 2 carbon dioxides. How many carbons in pyruvate?
3.
3. How many carbons in the subtle group? 2. So something has to happen between pyruvate and the subtle coenzyme A, or I'm going to lose a carbon. And then my 2 carbons here, they eventually end up there, but in the first round it's not the same carbons. They actually come from different places. Okay, so we are going to go through the whole thing. Hopefully we're going to make it through a equantities today. We'll see. So we're going to get from pyruvate to acetyl coenzyme A to citrate to isocitrate, and the rest of the wait for next time. But that is my whole cycle. So my 8 reactions in the cyclic part of it. And what's funny is that when people talk about the citric acid cycle, literally it's these 8 reactions, but sometimes this one also gets lumped in with it, the pyruvate to acetyl coenzyme A. But technically, this is not part of the cycle, because the whole point of the cycle is that your intermediates that you start with are the intermediates that you end with. They go first full circle. Okay, so I'm going to pyruvate to acetyl coenzyme A. This is performed by an enzyme that is a multi-enzyme complex. So it isn't really one enzyme, it's actually several enzymes, but usually we don't break it up into all the different reactions on paper, like what you just saw on the screen. It's just one step, and it's pyruvate dehydrogenase, but technically there's more than one enzyme. This has several advantages. When you start clumping all your enzymes together into one complex, closer together. So active sites are closer together. So why does that matter?
Whatever you like catalyzed enough time to go out.
Okay. So time is, well, that's kind of the second point, but let's stay on time up here for the moment. So this is going to be faster if I'm close together. You don't have to wait to diffuse. But then you mentioned something else there,
That you can pass it from one to the other.
which is good because,
No like side reactions and
okay, no side reactions. So we're passing our substrate directly from one enzyme to another. Okay, and there's one more.
Does that have to do with free energy?
Well, no, in the end, your free energy, the whole idea behind free energy is that it doesn't matter what pathway you take, the change is going to be the same. So that shouldn't change whether it's separate enzymes or complex. Any other ideas?
So like regenerate itself is the next enzyme that is used.
So we are going to see that in this one, that we're going to regenerate a used enzyme using another enzyme in the complex. But that kind of goes again with the everything happening faster. Coordinated control. Of regulation. So, I mean, you guys have been regulated to death at this point because we've just gone through all those allosteric activators and inhibitors and phosphorylation events that regulate glucose metabolism. And we're going to have a whole new set now for the citric acid cycle. But what's nice about this is that if all your enzymes are together in one complex, then you don't necessarily need to regulate all of them separately. You might have one inhibitor that inhibits the whole set, or one activator that activates the whole set. So you can coordinate the regulation that way. Okay, so we've got this multi-enzyme complex. There are 3 enzymes required. In the complex, and together they're all called pyruvate dehydrogenase. Although technically that name only describes the first enzyme in the series of reactions. So enzyme number 1 really is pyruvate dehydrogenase. And enzyme number 2 is dihydrolipoyl. Transacetylase. And then E3 is dihydrolipoyl dehydrogenase. But usually when people are talking about pyruvate dehydrogenase, they're talking about the whole complex and all 3 enzymes, usually. So the organization of the complex can vary by organism. But the example in your book is the one I think given for E. coli. And in that you have 24 E2s at the core. And then you have 24 E1s and 12 E3s that surround the core. So, yeah, and when each subunit is probably several hundred amino acids long, and so you're looking at tens of thousands of kilodaltons, if not hundreds of thousands of kilodaltons per subunit, and now you've got, 24, 12, do that math for me, 48, 60 of those. You're starting to work up into something that is in megadaltons in size, so it's millions of AMUs. So they're big. So your book has a figure where it's trying to show the assembly, which I'm not so concerned. And I think it's mislabeled. I think they need to write E3 and E1. That doesn't make sense to me. So because the core I have shown in green, you can see the core underneath there, and then it's supposed to be the E1s and E3s that surround the core. And then this is just a little space-fill model of the complex. So I just want to stress that they are very, very large. And they're large enough that you, by electron microscopy, you can see them. Kind of like when we talk about, well, actually later we'll talk about polysomes. You can see those as well. Ribosomes tend to be pretty big. So my overall reaction of the debate, I'm going to acetylcoenzyme. So this pyruvate plus the acetylcoenzyme plus an NAD. All the dehydrogenases, which means we're going to be moving some electrons around. And I'm going to end up with acetyl coenzyme A. And you already told me the acetyl group was only 2 carbons and pyruvate was 3. So now we're going to lose a carbon, CO2. And then we also get NADH. And whenever you reduce NADH, you also end up with a proton. We're going to see things written out in words a lot more often than in structures. We will go through all the structures in the citric acid cycle. But for example, coenzyme A, we will never draw that out. It's just too big and complicated. And so it will always be written out in text. Sometimes I might put the little CH3C carbonyl in there for the acetyl group, but typically we'll just abbreviate, just like ATP and ADP. Okay, so this reaction requires 5 steps. Three enzymes, 5 steps. So number 1, decarboxylation of pyruvate. This requires an E1 and a TPP isoethylamine, pyrophosphate. Okay. So this is not the entire TPP, this is just the part that matters for the mechanism. And this is bound then by E1. So E1 itself doesn't do much except hold the coenzyme in place so that it can do the chemistry. And I have my pyruvate coming in, and I'm going to decarboxylate it. When we've seen decarboxylation reactions in the past, what kind of catalysis has it been? Maybe that's not fair.
Lightly.
Sorry?
Lightly.
You say a little
Can we
louder.
see like the ligase to it in the pyruvate decarboxylase?
Oh, you're jumping ahead on me. We did see that, yes we did.
That's not what we want.
Yeah, but what type of catalysis? Covalent, yeah. And it's usually because you have to create some sort of situation that promotes bond cleavage, and that might be through a shift base, it might be something else. But that's what I have going on here, right? So I have my TPP, and this decarboxylation happens through covalent catalysis, and so I lose that carboxyl group. And now I have this hydroxyethyl group, which with this terrible carbanion thing, but I also got some poison stabilization going on there. Okay. And then I'm sorry, you ruined my clicker question here. So let's see, is everybody paying attention? So where have we seen the cofactor T? Sorry, TP. I think I put that in there. We had a lot of people with confusion tonight, so yes, if you heard what Stephen just suggested, it was a pyruvate decarboxylase that he saw us before, that was in the fermentation pathway. So much for that question. Okay, so it requires that pathway, it is similar to our pyruvate decarboxylase. And fermentation. And so now we're going to have a pyruvate plus an E1. And it's best if, what was I going to say? Plus the coenzyme. I think this one, to balance, you have a proton that comes in, carbon dioxide is going to leave. And now we have a hydroxyethyl that is bound to TPP, which is bound by E1. So my type of catalysis, the one on here is again what? Proton covalent. And my second step, I'm going to transfer hydroxyethyl. TPP down to E1. Okay, E2 is going to come in. My E1 plus my TPP are going to leave. And what I'm going to get is an acetyl dihydrolipoamide. That is down to E2. See that? That's the dash E2. So the dihydrolipoamide is not very descriptive of what the group looks like. The lipo tells you that there's going to be some big hydrophobic thing involved, and that actually is not the catalytic group that's involved. The catalytic group is this little ring structure at the end of the big fatty arm. And what does that look like? It looks like a disulfide, yeah. Great thing about disulfides is that you can oxidize and reduce them, and that's going to be important for the rest of the mechanism. But this is the hydroxyethyl group in red that came from my pyruvate, is now attached to the cofactor on enzyme 1. And basically, we're going to just transfer the hydroxyethyl group to this little disulfide thing by breaking that disulfide bond. So I end up with the reduced sulfur there. And I've got a little rearrangement going on. But then I'm left with the acetyl group, and I've released my E1 at that point. So it's my acetyl dihydrolipoamide. Alright, so then step 3. This is going to be transfer of the acetyl group to coenzyme A. So I have my acetyl dihydrolipoamide. That is covalently linked to E2. And then I have a coenzyme A coming in. And acetyl coenzyme A is going to leave. And I'm left with a dihydrolipoamide. This is just for E2. So here I am with my acetyl group that's attached to this lipoamide group. Coenzyme A comes in, and the only important thing about coenzyme A that you have to remember is that it has a thiol group on it, and that's how we connect it to things, is through a thiol. So, yay, the thiol group comes in, it attacks the carbonyl, I end up displacing that sulfur, and so what kind of reaction is that? So, in terms of organic lingo, not an SN2, this is it's a carbonyl. But it is a nucleophilic reaction, and it is a substitution reaction. There's the seal, yes, and the seal nucleophilic substitution. Yeah, SO2, so that's that's again with like alkyl halides, where you're substituting a bromo group for a chloride group, or sometimes with alcohols, where you're substituting nitrogens. But whenever you see it attacking carbonyl, it's in the seal nucleophilic substitution. Okay, great, so that comes in, and then we just lost our enzyme here. That is the product we're going for. So by the end of step 3, we have our acetyl coenzyme A, but again, this was 5 reactions and 3 enzymes, and we haven't even seen the 3rd enzyme yet, and the whole point of the last 2 reactions is just to regenerate our enzyme. That's all the rest of it is there for. So our acetyl coenzyme goes away, but this has been reduced, and we need to reform that disulfide in that ring in order to be able to perform this reaction again. So the rest will be to regenerate. Well, I might have a question here. Okay, so step 4. We're going to regenerate lipoamide of E2. And so my dihydro lipoamide, which is bound to E2, is going to be converted back into a lipoamide of E2. Okay. This is reduced. This is the oxidized form. And to do that, we need E3. And E3 in an oxidized form comes in, and then it's going to leave in a reduced form. And E3 also has something in here that is a disulfide. It also has a prosthetic FAD group in it as well. Here is my dihydrolipoamide, where I have those 2 reduced diol groups. I need to reform that little disulfide in between them, and so to do that, this gets oxidized. This gets reduced, so this disulfide goes away. So it's just kind of swapping around with electrons and hydrogens. A redox reaction. And then the next problem is that now we have this reduced form of E3, and we have to regenerate that. So step 5 is regeneration of E3. So I have my E3 in its reduced form. I'm going to turn it back into an E3 in its oxidized form. And to do that, we actually need NAD in its oxidized form, and it's going to get reduced. themselves. There is this FAD prosthetic group, and you actually do get transfer of those electrons to the FAD group first. So it was put in as an intermediate where we reformed double bond. And so it's actually the FAD that's going to transfer the electrons to the NAD. Yeah, but then NAD gets reduced, and I'm back to an oxidized FAD and an oxidized set of sulfurs. And now we're ready to do it all again. So there's the whole thing. So pyruvate comes in, gets decarboxylated, and the last two carbons get covalently attached to E1 as that hydroxyethyl group. Then that gets transferred to my lithoamide of E2. So here's my acetyl group. Then that gets transferred to coenzyme A. So there's my acetyl coenzyme A. But now this is still reduced, so we have to oxidize it. So E3 comes in, we'll oxidize it back. And then this ends up being reduced, and we reoxidize that. So we shuffle some electrons around, we'll eventually end up in NADH. Yeah.
Can you clarify the difference between like the coenzyme?
A cofactor is the same thing as a coenzyme if the cofactor is an organic compound. Then you can use those interchangeably.
Okay.
A prosthetic group is a coenzyme that, or it could be a cofactor, that is permanently bound to the enzyme, so you don't exchange it, whereas some coenzymes act as co-substrates. So for example, NAD here would be a co-substrate, but FAD is a prosthetic group because it never uses enzyme.
So, like a prosthetic group or a substrate, they can both be cofactors?
Well, your substrate's your substrate, so pyruvate is your substrate.
Oh, okay.
Okay. And it is coming through in red and eventually ends up as acetyl coenzyme A. But any other groups that are involved in the catalysis that are not enzyme are cofactors of some kind. And if they're organic as opposed to a metal, then they're coenzymes. And if they are permanently attached to their enzyme, do I need to write all this down? Would you like me to write all this down?
Yes, please.
So we'll just do just some definitions. And review cofactors. So a cofactor is a non-enzyme molecule or ion needed for catalysis. And this is not the substrate. And a coenzyme, this is a cofactor that is a small organic molecule. And a prosthetic group this is a cofactor that is permanently bound to its enzyme, so it's never exchanged. And a co-substrate, this is a cofactor that is transiently associated. With the enzyme. So it's not with the enzyme. So there is actually kind of a level between prosthetic group and co-substrate. You can have cofactors that are bound to your enzyme, but they can get swapped out over time, but it isn't part of the reaction. With a co-substrate, it's one comes in and it leaves afterwards. And we don't necessarily show how these things get regenerated. So we just reduce NAD, and it's going to be way downstream before the NAD is ever converted back to NAD. So it's important that the enzyme get regenerated and any prosthetic groups get regenerated, but your co-substrates don't have to get regenerated immediately.
The substrates might be like the side redox reactions, the couple, like the NAD.
Yeah, anything that comes in and leaves again. Yeah, so in this one, the only co-substrate is NAD. So NAD comes in and NADH leaves. My TPP is it is a cofactor. It is also a coenzyme, and it is this one. I'm not sure if it is covalently bound, so I'm not sure that it gets into the region of the prosthetic group. Whereas this FAD never leaves, and that's going to kind of depend on person to person is what they want to do. But this is coenzyme. The lipoamyl group, we're going to talk about that one next. It isn't really a coenzyme, it's a modification of the enzyme itself. So it's basically just a modified side chain. This was a lysine, and then we got this covalent modification at the end of it. So it's not really a coenzyme. It's part of the enzyme. I'm sorry to be wishy-washy with definitions. Some definitions are like that, but they overlap. So, transfer from E1 to E2 to E3. This is made possible by making a multi-enzyme complex. And it's also possible
Bless you.
because E2 has a swinging lipolysyl arm, and this thing is 14 angstroms long and very flexible. So if it wasn't, then you'd be in a situation where you would have to release substrates or have enzymes, like chemical proximity and leave again. That complex wouldn't work without this arm. So again, this is my lipoamide group up here. This is the thing doing the chemistry. It's that little 500 ring of the disulfide. The enzyme, again, is a lysine that has been modified with this little lipoamide group. And it's called a lipoamide group because it is an amide linkage that has connected this group. And lipo, because when you start looking at all these carbon, is very fatty and very hydrophobic. So that's where it gets its name. But this thing is pretty long, and it can swing back and forth. So it can swing over to E1 and do its thing there, and it can swing back over to E3 and get regenerated later. And so because that is flexible, it's basically moving active sites together and apart again. Just, yeah, that's really cool. Okay, so that gets us from pyruvate to acetyl coenzyme A. So we're going to do 10 minutes worth of citric acid cycle. Enzymes of the CAC. Number 1, citric synthase. Number 2, conitase. Number 3, isocitrate dehydrogenase. Number 4, alpha-ketoglutarate dehydrogenase. I'm not going to be using any abbreviations on these, we're going to stick with the whole names. 5 is a succinyl coenzyme A synthase. Number 6 is a succinate dehydrogenase. Number 7 is fumarase. And number 8, malate dehydrogenase. Okay, how many NADHs are we going to make in the citric acid cycle? And we looked at your net equation. We go all the way back to your overall reaction, 8 steps.
3,
3, how many FADH2s?
1,
1. How many dehydrogenases do I have here?
4,
4. Okay, so I'm going to reduce 3 NADs and I'm going to reduce the FAD, and I'm going to have 4 different reactions that are redox reactions, and they're all performed by dehydrogenases. So right off the bat, you know where those belong. Okay. So back to that overall scheme. We're right here. We have acetyl coenzyme A. And we're going to come in with our first enzyme, citrate synthase, and we are going to need an intermediate from the citric acid cycle to do that. We need oxaloacetate. So we're going to take acetyl coenzyme A, oxaloacetate, and we're going to make citrate. And then we're going to follow the way around. So here's my NAD getting reduced with dehydrogenase, NAD getting reduced dehydrogenase, FAD getting reduced dehydrogenase, and B getting reduced dehydrogenase. Okay. Step 1. This is condensation of acetyl coenzyme A to oxaloacetate. So acetyl coenzyme A plus oxaloacetate is going to make citrate, and then we're going to reduce our coenzyme A. We're going to start drawing these out now. So for the coenzyme A, again, we're going to abbreviate that, but we're going to show my bioester linkage to the acetyl group. And we're going to add that to oxaloacetate, which has a couple of carboxylic acid groups on it. And that's going to make citrate, which looks like this. That's my coenzyme A, and I'm going to go ahead and write the file this time. that functional group. mechanism, and you're going to tell me about it. Got it. Oh, having a aspartic acid, a histidine, and another histidine that are all involved in this mechanism. I have my oxaloacetate that has to come in. I also have my acetyl coenzyme A that has to come in. What is that aspartic acid doing?
It's acting as a base.
Base.
Base catalysis. Okay, aspartic acid comes in, does some base catalysis. In order to convert my acetyl coenzyme A, this group right here, from a keto, it's technically not a keto because it's a bioester, but something that looks like a keto group to something that looks like an enol group by removing that proton. Now, what is my histidine doing in the process?
Is it stabilizing through hydrogen bond?
Yeah, this is a good question. I don't know what they meant to draw here. Because it seems to be kind of ambiguous, because it shows the hydrogen being put over here as a perturbation, in which case is acting as an acid and it's acid catalysis. But for whatever reason, even though they decided to draw it in red, like it's associated here, they kept the negative charge on the oxygen and drew that as a dotted line. So I don't know what they meant to draw, and maybe it's because they don't know, and it could be either. It could be a proximity orientation, or it could be some sort of inductive effect that's going on, as opposed to actual proton transfer. But yeah, maybe acid-base catalysis, maybe it's just pulling it in place. But anyway, once I have this little enol thing, that can come up and attack the carbonyl of my oxaloacetate, and that's helped out by this histidine, which is doing what? Acid catalysis. Okay. So now I've joined my acetyl group with my oxaloacetate. I'm still bound to coenzyme A though. And so in the very last step, water comes in to hydrolyze that bioester bond, releases the coenzyme A, and now I have citrate. We're going to write a couple things down, but really quick, just make sure I know you can today. How would you classify citrate synthase? What kind of enzyme do you think that is? Everybody answered that master. Uh-oh, everywhere. Let's see, I would think the most misleading choice would have been the ligase, which is why I left it off. It's not even on here. Is the transferase. What am I transferring?
Everything.
An acetyl group. Yeah, so my acetyl group is the functional group that I'm transferring. That is a transferase. Can I write just a couple little things down quick? Please. 1 minute. Okay, so this is catalyzed by citrate synthase. It is mediated by acid-base catalysis via aspartate and histidine residues. And the other thing I want to mention is that this delta G, my standard frequency change, happens to be a negative 31.5 kilojoules per mole. And because of that, this is technically an irreversible step because it releases so much energy. And you might remember that coenzyme A conjugates are high energy compounds. I wanted to do conatase, but we got sidetracked a little bit on cofactors, and that's okay. But the reason I wanted to talk about a conatase today is because the reading assignment is all about the mechanism of a conatase. So we're not going to do the mechanism of a conatase in class. What day is it? On Friday? Okay. Instead, we're going to read the paper where they determine the mechanism for a conatase instead. So that's what's coming up.